Last time I stripped down this old Boxford CNC lathe. Removed all the electronics, cleaned, lubricated and made sure all the mechanical parts were working. Then gave it a nice new coat of paint. But it still doesn't work. Now I need to upgrade the electronics and control system to something a bit more modern. Like I did with the MCO mill, I want to fit everything inside the machine, so I don't need a separate PC or control box taking up extra space. Over the years, I've built quite a few different CNC machines. I've always used Mark III to control them, or even Mark II. Yes, I am that old. It's easy to use, does just what I want, and I've always been perfectly happy with it. But for this machine, I want to try something different. There are two main reasons for this. Firstly, this lathe is small and there's not as much space inside as the MCO milling machine had. I could probably still fit in a small PC, but I thought I'd try a Raspberry Pi instead. Raspberry Pis can't run Mark III, so I'd have to go with something like LinuxCNC instead. But the main reason for not using Mark III is that this lathe has a spindle encoder that I want to use to synchronize the motion of the carriage for doing things like cutting threads. Mark III can't do that, at least not as far as I can tell. It's probably possible with some additional hardware, but apparently this is the sort of thing that LinuxCNC is very good at. Now, I dabbled a little with Raspberry Pis when they first came out, but they were slow and unreliable, so I gave up with them. And I've never used LinuxCNC before, so it's going to be a steep learning curve. I've already removed all of the old electronics, and I'm starting with a blank slate. This aluminium panel, everything was previously attached to. First to go on is the Raspberry Pi. This is a Pi 4 with 8 GB of RAM. These stepper drivers are the ones I rejected from the MCO mill upgrade, as they weren't up to the job. The motors on this lathe, I'm keeping the original ones, are smaller, and I'm also running them at a lower voltage, so I'm hoping the drives will be okay here. If not, I can always upgrade them. There are 3 drives, one for the carriage, or Z-axis, one for the cross-slide, or X-axis, and one for the tool changer. Everything is going to be connected to the Raspberry Pi via the GPIO port. I'm using an opto-isolator board or hat in between. This isn't really essential, as most drives have opto-isolated inputs anyway, but it is useful for input signals that are at a different voltage, such as the inductive limit switches I'm using. And it also has LEDs that let you see the status of each pin, which is useful for debugging. To power everything, I'm using these 2 small switching power supplies. There's a 5-volt one and a 24-volt one. Incidentally, this thing that looks like a transformer isn't the original power supply. It's actually a choke that's used in conjunction with the spindle motor. This is the old transformer power supply. It's in working order and I could reuse it, but it takes up a lot of space together with its rectifiers and smoothing capacitors. The modern alternative is smaller and can also provide more power. I wanted to reuse the main control buttons on the front panel. Some of the other ones are for functions this machine doesn't even have. So I just wired directly to the buttons I need. After hooking up all the electronics, the wiring was starting to get a bit out of hand, so I did my best to tidy it up. This wasn't helped by the fact that with most of the electronics mounted on the door, a lot of the wires have to cross this hinge, so need to be able to flex. As I mentioned before, I'd like to keep the original spindle motor speed controller, as this would be quite expensive to replace. This type of lathe is known as a slant bed or back tool lathe. This means the lathe bed is at the back of the machine rather than the bottom. This has some advantages for a CNC lathe. The chips drop straight down into the removable chip tray rather than onto the bed, as they do with a regular lathe. It's also easier to see the tool insert as it's cutting, so you can see if it's damaged or gummed up. However, this means that the normal turning direction is the opposite way to most lathes. And if I want to use regular clockwise drills too, then the lathe needs to be able to spin in both directions. The speed controller fitted to the lathe is what's known as a single quadrant driver. It's basically a switch that can turn on and off very fast. The speed is controlled by varying the on time versus the off time. But single quadrant drivers can only drive the motor in one direction. Normally, to drive a DC motor in both directions, you would use a 4-quadrant driver. But these are a lot more expensive, so how have Boxford managed to get this single quadrant driver to spin the motor in both directions? What they've done is put a relay in between the driver and the motor. This is a much cheaper solution. What the relay does is mechanically disconnect both the motor wires, swap them over, and reconnect them backwards, all in around 10 milliseconds or so. When voltage is applied, this makes the motor now spin in the other direction. But if you know anything about electric motors and semiconductor drivers, you might see a problem with this approach. If you try and reverse the direction this way whilst the motor is still spinning, it's a bit like... and bad things can happen. A motor is really just a long coil of wire around an iron core, which means it has a large inductance. Once a current is flowing through it, it wants to keep on flowing at the same rate and really doesn't like being suddenly interrupted or changing direction. That's why this diode that appears to be backwards across the motor terminals is there. It provides a path for the current to keep flowing when the switch is open. Of course, the switch isn't really just a switch. It's some kind of transistor like a MOSFET, and these are sensitive to large voltages being applied across their output. Suddenly disconnecting the motor whilst it's running will cause a very high voltage to build up across the terminals. And as for then reconnecting this backwards to the speed controller, well... there is this large choke which is connected in series with the motor, which I believe might be there to limit voltage spikes, but suddenly disconnecting this whilst current is running through it could also be bad. So maybe its main purpose is limiting starting current or suppressing electrical noise. But I assume Boxford must have had some sort of safety system to wait for the motor to spin down before reversing direction. Unfortunately, LinuxCNC has no such system, out of the box anyway. It will let you change from forwards to reverse instantly, and it just expects whatever hardware is connected to be able to handle this. I'm sure it's probably possible to code this into LinuxCNC using ramps and delays. I could also just add a delay to my G-code programs whenever changing direction. But I really don't trust either of those solutions. I'd prefer something a bit more foolproof. So I built a circuit that goes in between the Raspberry Pi, the relay, and the speed controller. It intercepts the control signals and monitors the spindle speed using the encoder, ensuring that if the spindle is reversed while running, it's first powered down and the relay not switched until the motor has stopped. I also included a delay in case the belt between the motor and encoder is removed. LinuxCNC has a spindle at speed function which can be used to make it wait for the spindle to get up to speed before executing the next line of G-code. The circuit is based around an 8-bit microcontroller programmed in assembly language. I haven't said that for a long time. Let's have another look at that. Here, LinuxCNC sets the forward output and also the speed via the duty cycle on the PWM pin. The forward output is sent through to the relay. The relay is a twin coil latching type and only requires a short pulse to switch, so this output will turn off after a second or so. The speed signal is fed through to the speed controller, and the motor starts. Here the spindle reverses. LinuxCNC instantly swaps the outputs to reverse, whilst leaving the speed signal as it was. The filtered relay signals do not change yet. The speed signal is turned off. The circuit monitors the speed of the motor and waits for it to stop, plus an extra short delay. Then the relay is switched safely and the speed signal re-enabled. The motor now spins up in the other direction. LinuxCNC will pause executing G-code until the spindle encoder indicates the correct speed has been reached. Since I was measuring the spindle speed anyway, I thought I'd add a readout to the control panel. So I removed a couple of unused buttons and replaced them with a 7-segment LED display. LinuxCNC does display the measured spindle speed, but I prefer the LED readout, and it's a useful way to double-check everything is working. Having mostly finished up the electronics, it was time to move on to the software side. This was all new to me. It would take an entire very long video to explain how I set up LinuxCNC, so I'm not going to get too deep into this. Basically, I installed a real-time operating system on the Pi called Debian Bookworm, and a version of LinuxCNC written for the Pi, which supports its GPIO port for the inputs and outputs. I bought exactly the same touchscreen monitor that I used for the Emco mill, from the same seller, which arrived in the same box, but instead of Bunstruck, this one bore the illustrious moniker Prechen, and because it's a Linux system, of course I added a keyboard and mouse, which I put on a slide-out shelf under the machine. Then it was a lot of reading through documentation and examples to work out how to set everything up step by step. This took a while. LinuxCNC is mainly configured through 2 text files. The ini file, which sets basic parameters like how many axes are being used, their speed, acceleration, limits, etc., and other settings for LinuxCNC itself. And the HAL file, where you basically connect pins and signals and outputs together to make everything work. It's a lot like wiring up a physical circuit. I chose the GMOCCAPY user interface. Not sure how you pronounce that. This is designed for touchscreens and just made more sense to me than some of the others available. I was first able to get each axis to jog around using either the touchscreen or the panel buttons. The machine didn't have any homing switches fitted, so I added these inductive proximity switches. I wrote a macro to advance the tool turret by 1 position. I didn't add a switch to the turret to tell me what position it's in, as there wasn't a convenient place to put it. So I just need to remember to always start and finish in position 1. Eventually, I was able to get everything set up and configured the way I wanted. Nearly time to try and make something, but first, the lathe came with just this small 80mm chuck, and only the inside jaws. The largest diameter I can hold with this is only about 35mm. The lathe has a swing of 160mm, And whilst I'll probably never use all of that, it would be nicer to have a bigger chuck. A 125mm chuck would fit, but the jaws wouldn't be able to fully open. So the best option seems a 100mm chuck, which, though only slightly bigger, gives me a lot more holding capacity with the outside jaws too. So I bought a new 100mm chuck and promptly drilled holes through it. Since the chucks mount from the front with screws, I drilled the existing mounting holes on the back all the way through, so I could screw it to a backplate that itself screws to the spindle nose. I'd also like a small collet chuck for better repeatability. So I bought a second-hand ISO 40 ER32 holder for a milling machine and chopped the end off. I actually got this idea from the YouTube channel We Can Do That Better, where he did the same thing with his MCO Compact 5 CNC lathe. The MCO 5 has the same spindle nose as the Boxford, though I think he used an ER20 holder, which will hold up to 13mm. I used the bigger ER32, which can hold up to 20mm, which matches the spindle bore of the Boxford. Because I went with the bigger holder, getting the mounting screws in was more of a challenge. I had to shorten an Allen key to tighten them. About 1/100 of a millimeter run out at the far edge. Even less at the narrow end of the taper. That's good enough for me. I also added a backstop to the collet chuck for turning multiple identical parts to the same length. Okay, time now for a proper test. I'm going to try and make a chess pawn. This is kind of like a benchy for a CNC lathe. I can't reach into all of the details with this tool, so I changed to an opposite-handed one to finish it off. A quick polish on the manual lathe and it's done. Not bad. And now the whole reason I did everything this way in the first place, to be able to make coordinated moves with the carriage in sync with the spindle, using position feedback from the spindle encoder. Specifically in this case to cut threads, but it can also be used for other things, such as knurling. I'm doing this using the G-code instruction G76. This single G-code specifies multiple parameters to cut threads and takes care of synchronizing the motion. You can set the thread pitch, length, depth of each pass, angle the tool is fed in, number of spring passes, even taper the end of the thread. Yes, I know I really need a left-hand threading tool for this machine, but I haven't got one, so this will have to do. It's far too long as well. The tool is robbing slightly on the return. This is because I didn't set any thread peak offset. I still need to tweak things a bit. Definitely not the best looking thread in the world. I need to play around more with the settings. But the dimensions are correct, and it works just fine. So this has been quite a journey from a discarded, unloved old lathe to a functional, quite versatile CNC machine. I think it's going to become a very useful addition to my workshop.